Okay, so I've got a two-stage compressor with intercooling in there. Starts at an initial state and ultimately compresses to 12 kilopascals. In the middle, at 350 kilopascals, pulls it out, cools it back down to the 300 that it was initially, and then does the rest of the compression. What I want to do here is I want to find the power of this and compare it to the power if I had gone straight from 100 kilopascals all the way up to 1200 kilopascals. So that would be a compressor without intercooling. So we're going to compare those two. So as per usual, what we want to do is we want to find our H values. Okay, I can look up H1 and HD directly. Okay, because I know that's at 300 Kelvin. Now, 1 to C, D to 2, these are isentropic compressions. So I'm going to use the pressure ratios, those relative pressures, to figure this out. So I'm going to look up my relative pressures, use those relative pressures to find the relative pressure at C, find the relative pressure at 2, and then from that, look up my H value at C, H value at 2. Once I have those, I can then figure out the work done. So I'm going to start with that. Okay. So I'm going to start going to 300. 1 and D are essentially the same state. So I go to T equals 300. I get H of 300.19 and a PR of 1.386. And again, I'm using PR because of the isentropic compression, right? So I'm going to use that relative pressure ratio to figure this stuff out. Okay, so again, H1 is 300.19 and PR is 1.386. Same thing over here. Okay, so now I've got state 1 and state D. Now I'm going to use those pressure ratios, which is to say I'm going to calculate PRC over PR1, set that equal to PC over P1. Again, I know PC, I know P1, I know PR1. The only thing I don't know is PRC, which comes out to be 4.851. Now I'm going to use that relative pressure to calculate the enthalpy at state C. I'm going to do the same thing here. Okay, where I know PR2 over PRD equals P2 over PD. Now I know my actual pressure ratio. I know my relative pressure at D. I can use that to find PR2, where PR2 is going to actually be 4.752. Now, I'm going to use both of these guys to look up my H values, HC and H2. One's at 4.85, one's at 4.75. So they're actually pretty close in their enthalpy here. So I go over here, I go 4.85. So they're both going to be in between, in like the 420s for H values. And I actually get HC to be 429 and H2 to be 427. Again, using the relative pressure 4.85 and 4.75. So again, HC is 429.77. And H2 then is 427.21. Now, in order to find the work, okay, I am just going to get essentially, so the work of the compressor is just HC minus H1 plus H2 minus HD. Okay, so plugging those values into a calculator, I get I get 256.6, and that is kilowatts per kilogram. Actually, it would be That would actually be kilojoules per kilogram. Excuse me. Okay? So that's the work done by the intercooling one. Now, do the exact same thing going from 1 to 2. This is an isentropic compression, so I can look up this PR2 over PR1 equals P2 over P1. From that, I can learn that PR2, again, now I'm using a compression ratio of 12 to figure out PR2, and I calculate PR2 to be 16.632. Now using that, you're going to see that my temperature and enthalpy are going to be much higher. So going to 16.62, I'm way up here now. I'm in the 600 range. Okay, my H when I do my interpolation is actually 610.65. Okay, so the work of this compressor without the intercooling just goes H2 minus H1, which equals 610.65 minus 300.19, and I actually get 310.43 kilojoules per kilogram. Okay, so you can see more work is required with the direct compression as opposed to a compression with intercooling. Okay, and I decrease it, I don't know, what is that, about 20% or something? Maybe not quite 20%, but you get the idea that less work is done when I have the intercooling than when I don't have the intercooling. So that's the advantage of the intercooler, is that it requires less work to run the system, run the compressor.